Okay, so in this video, we will talk about the reactions of alcohols. In the first video, we already talked about the naming of the alcohols, the isomerism in alcohols, and the properties, physical properties of alcohol. Now we move on to the reactions. Now these are the some of the reactions. In addition to this, you will also do the oxidation of alcohols. So these are the reactions that we need to know. So let's just start with the reactions. The first reaction, combustion of alcohols. Now we know combustion means either you call it as a burning or you can also call it as a reaction with oxygen. Reaction with oxygen. Both are correct. So combustion means either you burn, you say burning in air or burning of a substance, or you say reaction with the oxygen. So like for example, if I'm taking any alcohol, the name of this will be ethanol. Eth means two carbon atom, N means the single bond between them, and all represents the functional group OH. You react it with oxygen, you will get carbon dioxide plus water. Now we already know from before that carbon dioxide is formed when it is excess. This is a complete combustion. Usually they don't talk about incomplete combustion in alcohols. So this is another important thing is, so this is a complete combustion. How do we know? Because carbon dioxide is formed. Another important thing is the delta H is negative over here. That means this is an exothermic reaction. This is an exothermic reaction. And this is one of the reasons why that ethanol is known as a biofuel. In some countries where they have enough of sugar cane or sugar, they convert ethanol into, they convert the sugars into ethanol, which is used as a fuel. So biofuel means they are getting, they are converting sugar, something which is grown, crops, renewable resource, into ethanol. So we have learned this. Ethanol can be produced by two different ways industrially, One is IGs, you have done this. One is through the fermentation process of sugar, and the other is hydration of ethene. Now both of these you have done in your IGCSE, so you will still need to know this. So in many countries, ethanol is legally mixed with the petrol and sold at the petrol station because it can provide energy when it is burned. The next reaction is dehydration of alcohols. Now the word dehydration means removal of water. So here, this will be, so what happens over here is you have, let us say, I'm writing ethanol this way just for our understanding, HNOH. So this is actually your CH3CH2OH. I'm writing it this way to explain you. Now, what happens over here is you react this in presence of either concentrated H2SO4 or you react it with in presence of concentrated H3PO4, that is phosphoric acid, or you can react it in presence of Al2O3. So all these are examples of dehydrating agents. All these are dehydrating agents. So under this presence of these, what happens is the H goes out, the OH goes out, and they combine to form water. So that is why you are calling it as dehydration, removal of water. And they in turn, this is not a mechanism, this is just to explain to you, and it forms CH2 double bond CH2, which is ethene. So you are starting with ethanol and you end up with ethene. You start with ethanol and with ethene. Important thing is any of these dehydrating agents can be used over here. And now a very common question that is asked in the exam is, what is the difference between a dehydrating agent and a drying agent. Now, drying agent, it removes water molecules. It removes H2O molecules. Like for example, you have CuSO4.5H2O. So if you want to remove this water, you will need a drying agent. So the salt becomes anhydrous. But the dehydrating agents, they remove H and OH from the molecule, which then combine to form water. So the molecule does not contain the water, but it is removing it. It is removing the H and the OH. Like over here, alcohol doesn't contain any water over here. But the dehydrating agents, they are removing the H and the OH. They in turn go and combine to form the water molecules. But here, water molecule as a whole is removed. Here, the H and the OH are removed. They then form the water molecule. So this is a basic difference. Some of the examples of the dehydrating agents already explained to you over here. And some of the examples of the drying agent could be like KOH, calcium chloride, silica, and calcium hydroxide. So these are some of the examples of a drying agent. Now, there are also questions about how do you carry out the dehydration of alcohol in lab. Dehydration of alcohol, or to be more specific, let's say ethanol. Dehydration of ethanol in lab. Basically, they want to see the setup. The examiner wants to see the setup. So this is the way you set up in the lab. You have a ceramic wood soaked in ethanol. That's one thing. Aluminum oxide is your dehydrating agent. And the delivery tube needs to go inside the collecting tube. This is your collecting tube. You are collecting the ethane gas over here. So now the important thing is the burner should heat both of them. So you should move the burner like this and this so that it heats this also and this. Now ethanol has a lower boiling point. So when you will heat it, its vapor will go and they will pass through the aluminum oxide. So basically the vapors of ethanol will go over the aluminum oxide dehydrating agent. They will lose the H and the OH, convert into ethene. Ethene will go over here. Now, initially the water is filled up to here. Now, gases being lighter, they will start collecting over here and they will push the water down. This is called as downward displacement of water. So the empty space at the top of the test tube or the collecting tube will give you the idea. It will give you the idea of how much gas has been collected. Now, the disadvantage of this method is, we already have done this before. The disadvantage is some gas may dissolve in water. Therefore, you have done this before in IGs. When you want to collect the gas, the best method is gas syringe. So you can show from here, you can show the gas syringe. So that's the next reaction, dehydration of alcohol. The third reaction is your formation of haloalkanes from alcohol. Formation of haloalkanes. Now, when I say haloalkane, it means we want a chloroalkane or a bromoalkane or a iodoalkane. Now there are several methods for them to make each one of them, but we will be talking about the best method for each one of them. That is according to your specification. So let's first start with the formation of chloroalkanes. How to make a chloroalkane. Now this is also called as a reaction with PCl5. This is also called as a reaction with PCl5. Phosphorus 5-chloride. That means the phosphorus has a oxidation state of 5 over here. Now, and this is a white solid. You need to know this. It is highly toxic, and the reactions are vigorous. Even at room temperature, the reaction is very explosive or very vigorous at room temperature itself. So in the exam, they have asked before, what is the state and the color of the PCl5? So let us take an example of ethanol again, CH3CH2OH, and you react it with PCl5. What happens is this OH goes out, one of the Cl will come over here. It will form CH3CH2Cl plus POCl3 plus HCl gas. So this is your chloroethane, which you want. This was our requirement. You started with ethanol. This POCl3 is called as phosphorus oxychloride, or it is also called as phosphoryl chloride. The important thing is this. This is observed as the observation because of this is steamy fumes. Now, because of this observation, this reaction is used as a test for OH group. Don't say test for alcohol. It's a test for the OH group. Now, why I'm specifying test for the OH group? Because if you add PCl5 to any organic compound, you add the PCl5 to any organic substance, and it gives you the steamy fumes. We have done this, how to check or test the steamy fumes. Right now from the reaction, I know it is HCl. It can be an alcohol, ROH, which is a representation of an alcohol. It can also be carboxylic acid, because carboxylic acid also have the OH group. So that is why you don't have to say that it is a test for alcohol. It is a test for the OH group. Both the carboxylic acid as well as the alcohols will give the positive test. Positive test means it will give you the steamy fumes. And this is especially useful for your unit 3. Especially useful for the unit 2. Just to show off the reaction with carboxylic acid, how does it happen? You have the OH. When you react with the PCl5, same way, this OH will be moved out. The Cl will come and takes its place. So this is a substitution reaction. And you end up with this plus POCl3 plus HCl gas. Again, steamy fumes. This group of compound which have COCl, you will study about this in A2. These are called as acid chlorides. Acid chlorides or acyl chloride, anything. So the importance of this reaction is it is used as a test for the OH group. Very important, the PCl5. Yes, I should have asked you over here What type of reaction is this? What type of reaction is this? Now here water is being removed. So this is an example of a elimination reaction. This is an example of a elimination reaction. While you don't need to know the mechanism. Mechanism is not required, as you can see in your specification. Description of the mechanism of these reactions are not required. But we are just understanding what type of reaction, not the mechanism. So, and this is your substitution reaction. This is your substitution reaction. Why substitution? The OH is being removed. The OH is being removed by the Cl or substituted by the Cl. Now, tertiary alcohols. So this reaction works good with primary and secondary alcohols. They react with PCl5, but the tertiary alcohols, they do not react with PCl5 in the same way. So that means if you are talking about the tertiary alcohol, we need a different method to prepare a chloroalkane. That means if I want to prepare a tertiary haloalkane, let us say this thing. If I want to make a tertiary haloalkane, the name for this will be, you will take this as a parent chain. You will take this as a parent chain. So you will name this as 2-chloro, 2-methyl, and propane. So I want to make this. So to make this, I need a tertiary alcohol. I need a tertiary alcohol, which will be this thing. So I cannot use the PCl5. So what we will do is we will react it with HCl. So what happens is the OH goes out, the Cl takes its place, and this OH and this H combines to, this is not a mechanism. So the Cl comes and takes its place here, and the water will be the additional product. So for the tertiary alcohol, will lead to the formation of tertiary haloalkane. So if you want a tertiary alcohol to change into tertiary haloalkane, you need to react it with concentrated HCl. That's the only thing, reaction for chloroalkanes. Then the next thing is bromoalkanes. The next thing is how to make a bromoalkane. Making bromoalkane. Now, bromoalkane, now the problem here is we don't have PBr5. PBr5 does not exist. So you don't have any such thing where you can make a, you can react the PBr5 with alcohol. So we need a different method. So here what we do is we take the alcohol, CH3CH2OH, that is ethanol, and you react it with HBr. You react it with HBr. But the problem is this HBr is unstable. Unstable means you don't have it in the lab. Like HCl you have in the lab, you don't have the HBr in the lab. So for such chemicals which are unstable, you don't have them in the lab. What you do is you go for in situ preparation. So we will have to go for the in situ preparation of HBr. Now the meaning of in situ means during the reaction. During the reaction. So you will not be adding HBr to alcohol. You will be adding something else that will make the HBr, and then the HBr will react. So how will the reaction take place? How will the reaction take place? So the reaction will be, so you have to take NaBr, react it with H2SO4. Now, important thing is it should be 50% concentrated, and then it will form KHSO4 and HBr. The HBr produced will then, in the second step, the HBr produced will then react with the CH3, CH2OH, where the Br will substitute the OH. The OH will come out, the H will come out, they will form the water molecule, and you will get the bromoalkane. Now remember, this is not a mechanism, this is just a way to understand what is happening. So you get your bromoethane. Now a few important things related to this. The first thing is how to carry out. It seems to be easy when we say it is in situ preparation, but how do we carry out? That's one thing. The second important thing is why we have said 50% concentrated. Now the reason is you have to recall your reaction of solid halides with concentrated sulfuric acid. Now if 100% concentrated H2SO4 is used, 100% I'm just using it. Otherwise, we say if it is more than 50% concentrated, what will happen is the HBr produced will further react with the H2SO4, which is concentrated H2SO4. It will react further. Or you say H2SO4 will react further, it is the same thing. So what will happen is the Br minus will change into Br2 and the H2SO4 will be changed into SO2. So when they react further, this will happen. So what is happening actually here? The Br minus is oxidation number of -1 and this is now 0. So this is an increase, which means this gets oxidized and the H2SO4 sulfur is +6 over here. It changes into +4, which means this is reduced. We already know that Br minus is a stronger reducing agent than Cl minus. We have studied this in the topic for halogens. So the Br, if you are using HCl, then it is not a problem. HCl does not react with the H2SO4 or any other thing, and we were not using the H2SO4 over there. The HBr is unstable, so you have to prepare it during the reaction, and because of that, you have to use the H2SO4. So that's why you have to use the 50% H2SO4. There's another way also out instead of so what is happening? I can also explain it in a way that we can say that the HBr reduces the H2SO4. You can say that thing, which is happening over here, or you can say the H2SO4 is oxidizes the HBr. So HBr reduces the H2SO4 to sulfur dioxide, or you say the H2SO4 oxidizes the HBr to Br2. Both is correct, and I have explained you based on the oxidation. The next thing is how are we going to carry this out? Now, like in situ preparation. So the way it is done is, I'm just trying to draw a rough diagram, is let us say you have a round bottom flask. So you will keep inside this KBr. It can be NaBr also. And your ethanol over here, there's no reaction between these two. So you will fill it with this KBr and H alcohol. And then using a burette, you can add your H2SO4. You can add the H2SO4. This is your burette. So as the H2SO4 drops down over here, what will happen is the H2SO4 and the KBr will combine together to make the HBr. So the HBr will be produced over here inside this. As the H2SO4 comes in contact with the KBr, once the HBr is produced, then it will start reacting with alcohol. So you're not adding the H2SO4, we are not adding the HBr, you are adding H2SO4 to KBr. They produce the HBr and then the HBr reacts. Now, you have to heat it or warm it. Now remember, these are alcohol over here, highly flammable. So there should be no flame near it. That's a normal thing for organic substances. No flame, Bunsen flame or any other flame near, and no flame near this. Why? The reason is alcohol is highly flammable. So this can be asked as a precaution in your safety thing for in your unit 3. So the easiest way is, then you will say, how do we warm it? So you can warm or heat it using a water bath, oil bath, sand bath, anything. The easiest thing is, if you don't remember, just say electrical method. So in an electrical method, you don't have any uh, any flame or such. The next is your iodoalkane. The next is your iodoalkane. Now for the iodoalkane, the problem is, as I said before, PCl5 does exist, PBr5 or PI5. These two, they do not exist. So we cannot use the PI5 over here like the first one. The other problem is the HBr we were able to use for the bromoalkane. This was used for the bromoalkane, but you cannot use the HI over here. The reason is HI is a stronger reducing agent. It's a very strong reducing agent. So it will reduce the even stronger reducing agent. It is so strong that it can even reduce the 50% H2SO4 which you were using before. And we have done this in your chapter for that reaction of solid halides with concentrated H2SO4. So we need a different method. And the different method is you react it with PI3. You react it with PI3, which is called as phosphorus 3 iodide. You react it with. Now again, the problem with this is unstable. You don't have this thing in the lab, so you have to go for in situ preparation. You already know the meaning of in situ preparation. So here, what you have to do is you have to take the this was your iodine. So here, what you have to do is you have to take a red phosphorus. So the formula is the same phosphorus. Phosphorus exists as many allotropic forms, red, white, yellow, and so on. So we have to take a red only, react it with iodine to form PI3, and then you can balance it. Yeah, so it is red phosphorus first. So you will take a phosphorus and iodine, and you will react them, and then this will then react with the alcohol. The PI3 which is produced, it reacts with alcohol, forming CH3, CH2I, which is what you want, ethane plus H3PO3 plus H3PO3. This H3PO3 is known as phosphorus acid. If you want to balance it, there are 3 iodines, so I have to put 3. Because of this, I have to take this 3. Now it is balanced. So this is how you prepare iodoalkane. So now, if I summarize what we are trying to do is that I want to make a chloroalkane. Now chloroalkane can be made by using PCl5. This is good for primary or secondary alcohol. Using the primary or the secondary alcohol, you can use the HCl, that is for tertiary alcohols, and you can use PCl3 also, but this is not in a specification, so we are not talking about this. It used to be before in the older specification, not now. So this was all about your chloroalkanes. We have talked about these two reactions. Then if you look at the how to form the bromoalkane, PBr5, it does not exist. So we are not talking about it. We are we have to react it with HBr, but HBr is unstable. So we take KBr plus concentrated H2SO4, which is 50% concentrated. And then we can take also red phosphorus and bromine to make PBr3 and then react it. But this is not in a specification, so I did not teach you. That was the reason we did. So for us, this is the only thing for bromo. And then for the iodo, alkane, iodoalkane could have, one of the method could have been PI5, but the problem is it does not exist. That's one thing. The second thing is you could have used HI, but we know this is a strong reducing agent. So we cannot use it. It can reduce it further. So instead of a stronger reducing agent, it can reduce even the 50% concentrated H2SO4. Sometimes they can also say use H3PO4. You can use H3PO4 instead of concentrated H3PO4 instead of H2SO4, then you can use it. So HI can be used in combination with the H3PO4, but this is not in a specification, so I'm not dealing with that. And then what we are dealing is the red phosphorus plus iodine forming PI3. So in your specification, what they have done is you have to study about this, how to make iodoalkane by using this method, bromoalkane by using the HBr method, and the chloroalkane by using the PCl5 and the HCl method. So the next lesson or the next video, we will talk about oxidation of alcohols. That should be next.